Here's an example that I think illustrates the three concepts that I've been talking about relating to zeros of polynomials. So here we have f of x is this polynomial, although it's in factored form. Most of the time we don't get the polynomials in factored form like this, but this one is already factored. If we were to multiply out this polynomial, doing all the foiling and distributive property that was necessary, we'd actually wind up with the first term of x times x times x times 3x times x times x, or 3x to the sixth power. Now we'd have a whole bunch of middle terms in here, an x to the fifth power, fourth power, third power, all the way down to x to the first and a constant. And that constant term that would be at the end, it would turn out that would be 5 times negative 7 times negative 4 times 3i times negative 3i. Now this polynomial has a degree of 6. That is the highest power of x that we see. And according to the fundamental theorem of algebra, that means that this polynomial should have 6 solutions. Let's check this out and see which solutions we can see here. Remember, each factor of this polynomial would give us a solution, just like if we factored a quadratic, we would see the solutions from each of the factors. So this means that one of the solutions is x equals negative 5. Then we get x equals negative 5 again. The next solution is x equals 7. This one's a little tougher because maybe we need to solve a little mini equation to make 3x minus 4 equals 0. We would need to have an x value of 4 over 3. So 4/3 is a solution. From this factor, we actually get an imaginary solution. The imaginary solution, x equals negative 3i. And here, the imaginary solution, x equals positive 3i. Now, how many solutions did we find? The fundamental theorem of algebra would tell us that we should get 6 solutions. Well, I see negative 5 twice. That means we have a solution negative 5 with multiplicity 2, and a solution of 7 and 4/3 and negative 3i and 3i. Since we get to count the solution that had multiplicity 2 twice, that's 2, 3, 4, 5, 6 solutions. And that is exactly what we'd expect based on the fundamental theorem of algebra. The degree of the polynomial is the same as the number of solutions of the polynomial. Remember the conjugate pairs idea. Well, my two imaginary answers are actually in a conjugate pair. This one could be thought of as 0 minus 3i, and this one could be thought of as 0 plus 3i. So my imaginary or complex answers came as a conjugate pair. Now, to apply the rational roots theorem, let me show you what all of the factors of the last number are. All the factors of 6,300. So it took me a while to list these out. It turns out there are 54 factors of 6,300. These are the two factors of 3, because remember our leading term was 3x to the sixth. So we have factors of the last, we have factors of the leading coefficient, and we create all the possible fractions where we take last over lead. So I've listed a few of them here. I would take the factor 1 over 3 and the factor 1 over 1 and 6,300 over 3 and 6,300 over 1 and 2 over 3 and 2 over 1 and 3,150 over 3 and 3,150 over 1, 3 over 3, 3 over 1, 2,100 over 3, 2,100 over 1. I'm just working my way down this list, taking factors of the last number or the constant over factors of the leading coefficient or the 3. This list would include 108 different possibilities, and that's only half of the what we call the usual suspects, because we could have the positive or negative versions of any of these fractions. So now our list of 108 turned into a list of 216 possible rational zeros. Now, not every one of these turns out to be a zero of the polynomial. Of course, we don't have 216 answers, But if we do look back at the solutions we got, we have an integer of -5, another integer 7, a rational number 4/3. All of these should be able to be located in that list. 5 over 1, taking the negative version of that, that would be -5. That solution's repeated twice. 7 over 1. That would give us our solution of x equals 7. And if we take the 4 over the 3, remember a factor of the last over a factor of the lead, 4 over 3 gives us that rational solution that we have. So that means a whole lot of these possible rational roots are not actually rational zeros of the function. And it turns out before computers, before graphing calculators, and a lot of the technology we have today, this is what maybe a mathematician would do for an afternoon's work. Maybe somebody needed to know what the roots of some polynomial were. And a mathematician might sit down and list all of the factors of the last and all of the factors of the lead and use synthetic division to test each one of them until they found the rational roots, the rational numbers that actually did create a zero for that polynomial. This next example illustrates a little better how we'll actually use these concepts related to roots or zeros of a polynomial. This time the question is phrased, find all solutions of the equation, but remember that's the same as the zeros of this polynomial or the roots of this polynomial. And so let's start out with the rational roots theorem. So I noticed that 12 is my last number and 2 is my leading coefficient. I'm going to come over here and make all the possible fractions out of factors of 12 over factors of 2. Factors of 12 would be 12 and 6 and 4 and 3 and 2 and 1. Factors of 2 are just 2 and 1. So I'm going to start forming fractions. 12 over 1, 12 over 2, 6 over 1, 6 over 2, 4 over 1, 4 over 2, 3 over 1, 3 over 2, 2 over 1, 2 over 2, 1 over 1, and 1 over 2. And remember, our possible solutions could be the positive or negative versions of any of these numbers. Now, I'm not going to go through and actually test each of these to see which one is a zero. I'm just going to get a graphing calculator out and see if the graphing calculator will show me any of the zeros. On my graphing calculator, I've already put the polynomial into my y equals. And what I'm going to use the rational roots theorem for is to set a decent window. I noticed that the biggest number I have in all of these is the number 12 over 1. So I'm going to make my window reach from, say, -13 to +13. All rational roots will have to be within this window. So let's take a look at the graph. My graph shows 3 zeros. Let's see if they're all rational zeros. With the list on the left, I can make some pretty decent guesses as to what these zeros might be. I look at this number here on the left, it sure looks like -2, and -2 is one of the fractions that is available to me. So let's check and see if -2 is a zero of the function. Yes, it is a zero or an x-intercept. So x equals -2 is one of my solutions. This next one over here is some kind of a fraction. Now what fraction? Well, the only fraction I see here that's between 0 and 1 is the fraction 1/2. Let's see if 1/2 is a zero of my function. Yes, it is. And finally, we've got a number out here. It looks like it's 4 or 5 or 6. Now, looking at the possibilities, it could be 4 or it could be 6, but not 5. 5 is not in this list. So let me check 6. And yes, that happens to be the third zero of my function. My graph has shown me 3 zeros, 3 solutions to this equation. X equals -2, x equals +1/2, and x equals 6. Now, according to the fundamental theorem of algebra, This polynomial with degree 3 should only have 3 solutions. So I'm not going to continue looking for any other solutions. I'm not going to test to see whether any of these other fractions will make the polynomial equal 0. I've found all of them already. This particular polynomial does not have any complex solutions, so I don't need to worry about the conjugate pairs theorem. So for this example, the directions are find all of the real or complex zeros of the function. And we've got, again, a polynomial down here. We've set it equal to 0, so we're solving this equation, trying to find all the zeros. Once again, we could start listing out all of the possible fractions that are the usual suspects, the possible rational roots. The factors of 50 are 50, 25, 10, 5, 2, and 1. The factors of 2 are 2 and 1. Let's see what a graphing calculator would show us as far as the solutions to this equation, or the x-intercepts or zeros of the function. So I've already entered the polynomial into my y1. I'm going to start with a zoom 6, that's zoom standard. That is a 10 by 10 window. And let's see what our graph shows. I see one solution there, and the graph is coming back up. I see a second solution. I only see 2 solutions. This is a polynomial of degree 4. A polynomial of degree 4 should have 4 solutions. So where are the other solutions hiding? Well, remember, the constant is a 50 and the leading coefficient is a 2. So as far as the possible rational roots, we could possibly have 50 over 2 or even 50 over 1 as a possible rational root. So it may be that the other solutions are hiding way out here to the sides. So just to check, I'm going to set my window, and I'll go a little bit above and a little bit below. So I'll make my lowest number here a negative 55, say, and a positive 55 for my highest number. That would be sure to include the biggest number I could get when I take last over lead, 50 over 1. And we'll see if those other 2 solutions were hiding out here on the edges. Well, there's the graph, and the graph has finished drawing, and I didn't see any more solutions. So no, these solutions are not hiding out here. Let's go back to a zoom 6 and see if we can determine what these zeros are. Remember that your calculator can find zeros. Maybe this would be a good time to review that skill. We hit second, trace, find a 0, and enter in a left bound and a right bound. I'm going to try to find that 0 on the left. So a good left bound might be negative 2.5. A good right bound might be negative 1 or so. And the solution in between there is negative 2. This other one looks like it's between 2 and 3. Second, trace, find a 0, and I'll set my left bound as positive 2 and my right bound as positive 3, and the 0 happens to be right in between, 2.5. And could I get 2.5 using a factor of 50 and a factor of 2? Well, yes, I could take 5, which is a factor of 50, over 2, which is a factor of 2. So that again fits with the rational roots theorem, 5 over 2 as a solution, or 2.5. So let's summarize what we know so far. Our zeros that we know so far are x equals negative 2 and x equals positive 2.5. And we still have the problem that we haven't found all those solutions. Remember, the fundamental theorem of algebra told me I should have 4 solutions. I only have 2 so far. So how are we going to find those extra solutions? Well, let's go back to that old friend of ours, which is synthetic division. And I'm going to set up a synthetic division for negative 2. The coefficients are 2, negative 9, 4, 35, and negative 50. So I'll quickly run through synthetic division. 2 times nothing is 2. Negative 2 times 2 is negative 4. Negative 4 and negative 9 is negative 13. Negative 2 times negative 13 is 26. 4 and 26 is 30. Negative 2 times 30 is negative 60. 35 and negative 60 is negative 25. Negative 2 times negative 25 is positive 50. And we get a remainder of 0, which is exactly what we were expecting. Now I'm going to take this solution and I'm going to do synthetic division with the 2.5. And let's do synthetic division again. We're going to get 2. 2.5 times 2 is 5. Negative 13 and 5 is negative 8. 2.5 times negative 8 is negative 20. 30 and negative 20 is positive 10. 2.5 times 10 is 25. And look at that. Our remainder, once again, came out 0. But how is this helping us? Well, remember when we did synthetic division with a 4th power polynomial, our solution was a 3rd power polynomial. When we did synthetic division with this 3rd power polynomial, our solution is a quadratic, the quadratic 2x squared minus 8x plus 10. Well, our remaining solutions are the solutions to this quadratic. Now, it turns out this quadratic cannot be factored. So our other alternative is to use the quadratic formula. Remember, when I do the quadratic formula, I like to do b squared minus 4ac first. In this case, that is 64 minus 4 times 2 times 10, or 64 minus 80. Well, b squared minus 4ac is negative 16. No wonder these solutions are not showing up on a graphing calculator, because my determinant is negative. When I set up the quadratic formula, I'm going to do opposite of b over 2 times a, and I'm going to do plus or minus the square root of negative 16, also over 2 times a. So we have 8 over 4 plus or minus, and the square root of negative 16 is 4i, also over 4. So there we go. We found our remaining two solutions, 2 plus I and 2 minus I. And notice that these two complex solutions came as a conjugate pair, 2 plus I and 2 minus I. So we now have all 4 of our solutions. Since this polynomial has degree 4, we know we can stop now. We found all the solutions. This next example asks a slightly different question. Whereas before we've had a polynomial and we were finding the zeros, this time they tell us what the zeros of the polynomial are, and we are supposed to build that polynomial. Well, let's see what they've told us. We have a 0 of 3 and another 0 at 2i, and we want to create the polynomial that has those zeros. Well, we're going to use the fact that for each 0 of a polynomial, there is a factor. Remember, if 3 is a 0 of the polynomial, then x minus 3 is a factor of the polynomial. And if 2i is a 0 of the polynomial, then x minus 2i is a factor of the polynomial. Now, another thing we have to remember is that complex zeros come in pairs. So not only should we have the complex number 2i, we should also have the complex number negative 2i. And that means we also have a factor of x plus 2i. So our polynomial f of x must have the factors x minus 3, x minus 2i, and x plus 2i. We'll worry about this fact, f of 4 equals 40, a little bit later. Let's find out what these 3 factors would multiply out to. Whenever I'm multiplying these factors, I'm going to take the 2 complex factors and multiply them first. When we do, we'll get x squared plus 2ix minus 2ix minus 4i squared. The complex parts of this cancel out. A minus 4i squared is the same as a negative 4 times a negative 1. So this is x squared plus 4. I'm going to multiply that times this other factor, x minus 3. And let's see what we get when we FOIL this. That is x cubed plus 4x minus 3x squared minus 12. Well, here we go. We've got a polynomial that has a zeros 3, 2i, and negative 2i. But we also have this other fact to contend with. F of 4 equals 40. So if I plug a 4 into this polynomial, I'm hoping I'm going to get an answer of 40. If not, we will make an adjustment. So let's see if this polynomial comes out to 40 with an input of 4. And 4 cubed plus 4 times negative 4 minus 3 times 4 squared minus 12 comes out to, oh no, only 20. But we were supposed to get a solution of 40. So how can we fix that? Well, 40 is 2 times 20. So what I need to do is I'm going to multiply this entire polynomial times 2, and that should fix our problem. 2x cubed plus 8x minus 6x squared minus 24 will have a value of 40 when we plug in the number 4. So this is the polynomial we were after. It has zeros of 3, 2i, and negative 2i, and f of 4 is equal to 40. My final example is pretty similar to the last problem, but the wording is slightly different and the algebra involved is a little more heavy duty. So try and stick with me as I solve this one. It says find a polynomial equation of least degree with integral coefficients that has negative 2, 3, and 1 plus 2i as solutions and leading coefficient 1. First thing I'm going to notice is that I have a complex solution, 1 plus 2i. That also means that I have its twin, right? Its conjugate pair. 1 minus 2i is another solution. So I'm going to have a factor of x plus 2 for the solution negative 2, x minus 3 for the solution 3, x minus 1 plus 2i, and x minus 1 minus 2i. Now, how am I going to multiply all those out? Well, here's a little trick. We're going to, first of all, focus on the hard part, the ones with these complex solutions. I'm going to write this as x minus 1 and minus 2i, so I distributed that negative sign, and the other factor, x minus 1 and plus 2i. Again, I distributed that negative sign. And I'm going to multiply this by doing x minus 1 times x minus 1. That's like first times first. And I'm going to multiply negative 2i times positive 2i. That's like last times last. And it turns out the outsides and insides will all cancel out. X squared minus 2x plus 1. That's what I get when I FOIL x minus 1 times another x minus 1. And then minus 4i squared. That's what I get when I multiply negative 2i times positive 2i. I could also write that negative 4i squared as a positive 4. So this all works out to x squared minus 2x plus 5. Now, x plus 2 times x minus 3, that's not too difficult to FOIL. That is x squared minus 1x minus 6. You can check that yourself. Well, we're getting there. Now we still have to multiply x squared minus x minus 6 times x squared minus 2x plus 5. To do that, I have to distribute the x squared through everything in the second parentheses, and minus x times everything in the second parentheses, and negative 6 times everything in the second parentheses. When I distribute the x squared through the second set of parentheses, I'll get x to the fourth minus 2x cubed plus 5x squared. When I distribute negative x through the second set of parentheses, I get negative x cubed, positive 2x, and negative 5x. When I distribute the negative 6 through the second set of parentheses, I get negative 6x squared plus 12x and minus 30. All combined, this is equal to x to the fourth minus 3x to the third plus 1x squared plus 7x minus 30. But this does not answer the question. Because the original question was to find a polynomial equation with these solutions. What I've written here is not an equation, so I need to add one extra detail. The equation is this polynomial equal to 0, and that equation has all of those solutions and a leading coefficient of 1.